All right, so now we're still doing implicit differentiation, just working through another example. I'm solving another equation that's given implicitly, where y is given implicitly as a function of x. Sine of xy equals cosine of x plus y. And again, the approach is the same. Notice there's y's on both sides of the equation this time. But basically all I'm doing is taking the derivative with respect to x of both sides, d dx of sine of xy equals d dx cosine of x plus y. Okay, now look at what's inside here. So it's a composite function, sine of xy, and the xy in here is a product. So I'm going to be using the chain rule in a sense, but also the product rule in this process. So dealing with my left-hand side, outside function is sine. That means its derivative would be cosine. Then I leave the inside function alone, cosine of xy. But then what I do is I multiply by the derivative of the inside function, and that is a product, so I would need the product rule. First function times the derivative of my second, so x times the derivative of y, which would just be dy dx, okay? And then the second function times the derivative of the first, so I'd have plus y times the derivative of x with respect to x. That's just 1, so I'm going to write y. Okay, working with my right-hand side, equals the derivative of cosine, my outside function would be negative sine. Leave the inside function alone, but then multiply this by the derivative of the inside function. The derivative of x is 1 plus the derivative of y, which is dy dx. Okay, and once again, our goal here is to isolate the dy dx so that we have that solved for. I need to distribute these trig functions into both sets of parentheses here. So this guy first will give me x dy dx cosine of xy plus y cosine of xy. Right-hand side, I'm going to get negative sine of x plus y times 1, so it's just this, plus dy dx. Actually, sorry, let's make that negative since I'm multiplying a negative y, sine of x plus y in, times sine of x plus y. Okay? Now we need to collect our dy dx terms on one side of my equation while everything else goes to the other side. So I'm going to start by adding this term over and subtracting this term over there. So that's going to give me x dy dx cosine of xy. Remember, I'm adding this term over, so it's going to be plus dy dx sine of x plus y equals negative sine of x plus y minus this term. I'm subtracting that over, minus y cosine of x y. Okay? I'm going to do two steps in one here. Notice I would be factoring this dy dx out. Actually, you know what, since this is only our second example doing something like this, I'll go ahead and write the step in also. X times cosine of xy plus sine of x plus y equals negative sine of x plus y minus y cosine of xy. Okay, last step is to divide everything by this big set of parentheses here so that the dy dx is by itself. And notice I have a negative in each term here. I'm going to go ahead and do what I did before and factor the negative all the way out so that I can write sine of x plus y here minus y plus y cosine of xy over this guy right here, x cosine of xy plus sine of x plus y. Let me double check my work here, make sure I didn't make any silly mistakes. No. Okay, I think we're good. So this would be our answer. Rather complicated looking, but the benefit of using implicit differentiation here is that if you actually look at each one of these steps, none of them are super outside the box or exceptionally difficult. It's just kind of a lot of writing. But the bigger benefit is that we didn't have to isolate the y to do the derivative. That would have been probably impossible in a case like this. Okay, here's a fun example. So this one, we're given an equation, but we're told that it would represent a rotated ellipse. So the equation is x squared plus 2xy plus 4y squared equals 12. And here's the graph of that rotated ellipse. Ignore the line for now. That's a line that we're going to find in this problem. It says find the points at which the ellipse has horizontal tangents. Remember, an equation will have, or a curve will have a horizontal tangent anywhere that its derivative is equal to 0. So, also, if you haven't covered rotated conic sections, that's fine. We're trusting that this equation does give us this graph. But in pre-calculus or college algebra, an optional topic that some people like to teach is rotated conics. So you may have seen stuff like this before. So the first thing I want to do is recognize that in order to find horizontal tangents, I'm looking for places where dy dx is equal to 0. So that means the first thing I would need to do is find dy dx. So I'm going to do what I've been doing, differentiate both sides of this equation with respect to x, plus 2xy plus 4y squared equals d dx of 12. Now that we've done a few examples of this, I'm not going to talk through my steps as intentionally. I'm just going to work through what both sides of these would look like and make sure that you're understanding where I'm getting this from. So this would be 2x plus 2x dy dx plus 2y plus 8y dy dx equals 0. Once you've practiced this a few times, you should be able to do what I just did about it as quickly as that. Now, as before, we're going to collect my dy dx's on one side of the equation and then get everything else over to the right. So I'm going to have 2x plus 2, whoops, I'm looking at the wrong thing. 2x dy dx plus 8y dy dx equals negative 2x minus 2y. I can do a couple of steps in one here. One thing I'm noticing is that every single term has a common factor of 2, so I might as well divide everything by 2 just to give me a little more simplification here. This would become a 4. So now if I were to factor that dy dx out, I'm going to have x plus 4y left over, which I know I'm going to be dividing by. So this will give me dy dx equals negative x minus y, or I could write this as negative x plus y, like this, over x plus 4y. Okay, now this is my derivative, and as we've been seeing, it depends on both x and y, because for any given x value here, most of the time I'm going to have 2 corresponding y values, so knowing the y value is also important. But in particular, we're interested in horizontal tangents. In other words, when is this thing equal to 0? Well, this is equal to 0 only when x plus y, my numerator, is equal to 0. Or, said differently, when y is equal to negative x, if I solve for y here. So this indicates that if I'm going to have any points on my ellipse where the tangent line is horizontal, it's going to coincide with points on the line y equals negative x. And that's the blue line that I've drawn here. Okay, so notice y equals negative x hits this ellipse in 2 points. And you can see from the graph, it looks like those points would actually have horizontal tangent lines. So what I'm going to do, rather than rely on a graph to tell me this, I'm going to take this result and use it as a substitution in the original equation up here and try to find those points algebraically. So I'm looking for points on the ellipse where y is equal to negative x. That means anywhere I see a y up here, I can substitute a negative x. That would give me x squared plus 2x times negative x plus 4 times negative x squared equals 12. Okay? Let's simplify. X squared, 2x times negative x would be minus 2x squared. Negative x squared is the same thing as x squared, so this is plus 4x squared equals 12. That's 5 minus 2 is 3. X squared equals 12, which means x squared equals 4. Whoops, I'm off screen there. X squared would equal 4. Solving this gives me x equals plus or minus 2. And if you notice from my curve up here, the x-coordinate of this point is 2, and the x-coordinate of this point is negative 2. So I'm getting what I'm expecting to see down here. Now, I need points, not just x values. But again, we said that the points at which we have these horizontal tangents will be on this line. So y equals negative x. If x equals positive 2, then the corresponding y value would be negative 2. If x equals negative 2, then the corresponding y value would be negative 2 or positive 2. And those actually are the 2 points that we see up here. Okay? So that's kind of a fun problem. It's a little less direct than, find the derivative and plug in this specific point. Let's go ahead and do one last problem before we wrap this section up. So far, the implicit differentiation we've been doing has been a means of finding dy dx, right? So finding the derivative of some function with respect to x, where that function has been given to us implicitly. What I want to do here is show that I can find the second derivative of a function using implicit differentiation as well. So in order to do that, we've got x squared plus xy plus y squared equals 3. And our goal here is to find y double prime. So I'm going to do the same thing that I've been doing. Find dx of both sides, x squared plus xy plus y squared equals dx of 3. And then differentiating both sides, my left-hand side will be 2x plus x. I've been writing dy dx, but because I'm using prime notation here, just for consistency, I'll call that y prime. I'm using my product rule here, by the way. So x times y prime plus the derivative of x times y, that would be plus y plus 2y y prime. Again, chain rule on this guy is where that y prime is coming from. This is equal to 0. Okay, now what I want to do is solve for y prime. So again, I'm going to have xy prime plus 2y y prime equals negative 2x minus y. I subtracted those two terms over. Y prime is equal to negative 2x plus y over x plus 2y after factoring those out. Okay? So now what I want to do is find my second derivative. And I can do that by differentiating both sides of this with respect to x. So if I do d dx of this side, d dx of that side, I'll end up with y double prime on my left. But what about my right? Well, I can take the negative out completely, and I'm stuck using the quotient rule here. So I use my bottom function times the derivative of my top, x plus 2y, times the derivative of the top, that would be 2, plus the derivative of y, which would be y prime, minus the top function times the derivative of the bottom, so minus 2x plus y, times the derivative of my bottom function, 1 plus 2y prime, okay? All over my bottom function squared, x plus 2y squared. Now you don't want to leave the y primes in there as they are, because what this should look like is only an expression involving x's and y's. So what do you do to get rid of the y primes here? Well, we have actually already found y prime in terms of x and y. So anywhere I see a y prime showing up here, I can substitute this expression for it because this is what y prime is equal to. We'll do that up here. So I get this, y double prime equals negative x plus 2y times 2 plus y prime, which was this. There's actually a negative there, so let me write that as minus 2x plus y over x plus 2y minus 2x plus y times 1 plus 2 times y prime. I can multiply the 2 into my numerator here, and I get 4x. Man, I'm really squeezing this in there. I'm also forgetting the negative there as well. I need to make sure I'm including the negative. Let me try this one more time. I'm making this kind of sloppy. I didn't leave enough space. Y double prime is equal to negative x plus 2y times 2 minus 2x plus y over x plus 2y minus 2x plus y times 1. Have to include the minus, and I'm going to multiply a 2 in there as well, so minus 4x plus 2y over x plus 2y all over x plus 2y quantity squared. Now there's probably a lot of simplification I could be doing with this, but for the sake of time I'm not going to worry about that, because the point of this was to see how to find y double prime having already found y prime using implicit differentiation. So it's messy. I could probably make this look better, but I'm just going to leave it like that for now. Okay, let's go ahead and stop this video here.